Hello and welcome to part 3 of the General Motors 8L90 transmission series. This is part 3 of a 7-part series, and in this part we're going to talk about the hydraulic operation. In part 1, I've broken down into 3 separate videos where we talked about the overhaul, the disassembly, assembly, and then the valve body. And then part 2 was all about mechanical and power flow. And then this one, being hydraulic, we're going to focus on all the hydraulic elements of this transmission. And this lecture is really going to be comprised of these separate topics: the regulation valves, torque converter clutch valves, the oil pump, the solenoid hydraulic control, the solenoid accumulators. We're going to look at some of the checkballs that they've got, really just pretty much where they go, do some vacuum testing, and then also look at this device there at the bottom. It's called a surge accumulator. So starting out with the upper valve body, these are the valves that you'll find in that valve body. I've got them disassembled and kind of laid out. We're going to talk about a few of these things more specifically. This clutch exhaust backfill is kind of an interesting valve there, and you're going to see that it pretty much holds some pressure into clutches when they're not applied. We're going to look at the torque converter clutch valve, the lubrication regulator valve, the torque converter clutch control valve, and then on this end we've got the default override valve, actuator feed limit, which is a pretty common valve that we see in a lot of General Motors transmissions, really any transmission that has solenoids. And the line pressure relief valve, that's a big spring with a ball behind it. And then the pressure regulator and the shuttle valve. And the shuttle valve is something we'll pay close attention to because some of the aftermarket companies have created a replacement or drop-in item for that shuttle valve. And then this picture just pretty much shows it at a different angle. This is our default override valve. If you take a look at this end plug here, it's got like a little stem on it, and that actually faces out. This actuator feed limit valve is not that uncommon. We see that in a lot of different transmissions, and they feed the solenoids with pressure. Not every solenoid in this transmission, but many of the solenoids are fed through AFL, actuator feed limit. And there's a spring, healthy spring, that kind of works with that valve to create actuator feed limit pressure. And then this is our line pressure relief valve. So if our line pressure ever gets too high, that will lift that ball off of its seat and relieve that pressure. And this is our pressure regulator valve. So we've got a pressure regulator valve, and then down here we call that the shuttle valve, not to be confused with the boost valve. We see a lot of transmissions, a lot of these GM transmissions have these aluminum sleeves that have a boost valve in there. That's not what this is. Now, line pressure does come around and sample on the end of this valve, and it does work up against this pressure regulator valve, but like a traditional boost valve where you might have a solenoid working against that boost valve, they don't do that on this. This is just a small valve that line pressure gets delivered into and works on this. We'll look at these fairly close, so this isn't going to be the last you hear of these different valves. Looking from the other side, once again, there's my clutch exhaust backfill, they call it, and it looks kind of like a pressure relief valve like we saw on the other side of the valve body with the line pressure relief valve, and it is. It's just a check ball that's got spring force behind it, and the pressure that leaves this circuit here is going to fill what they call their clutch exhaust backfill circuits. And any clutch that's released, if it has the provision for it, is actually going to be filled with this clutch exhaust backfill. And then we have our torque converter clutch valve, our lube regulator valve, and our torque converter control valve. Some of these valves you're going to see are addressed by these shift kits that these companies have, like the TransGo shift kit for the 8L90, or the zip kits, or just the individual valves that you can replace with Sonnax. Now, looking at that actuator feed limit, if you've worked on General Motors transmissions, you'll know that the actuator feed limit circuit is nothing new. This has been around. We see them on pretty much any electronically controlled transmission. And the term actuator feed limit can kind of be misleading. It's really a solenoid feed limit. So what it does is it receives line pressure, and that line pressure finds its way into the AFL circuit. And you can see the arrows kind of going around. And you can see that pressure goes through this orifice number 12 and works against the end of the actuator feed limit valve. So once enough line pressure finds its way into the AFL circuit, it will actually work up against that end of the valve, the reaction end of that valve, and eventually move its way over and cut off the passage that feeds it. Now, historically, the actuator feed limit circuits on these transmissions, on these GM transmissions, have had issues, basically with bore wear. The actuator feed limit spring is a fairly stout spring. It usually has quite a bit of tension on it. And coupled with the fact that this is a balance valve, which means it's always balancing spring pressure and the pressure that it lets into the circuit, in this case the actuator feed limit pressure here. It's balancing these two. Once this actuator feed limit pressure gets up high enough, it cuts itself off, and then when pressure bleeds down, the spring returns it over, and then that lets more line pressure into it. So the fact that it's living in this position right here and maybe oscillating back and forth causes all the wear to occur pretty much where we see this valve positioned. And if this passage right here, if this part of the valve body bore wears out, if you take a look, what's right next to this AFL circuit here is the exhaust. Any fluid that's in there could exhaust out. And then that means we would get an overall lower AFL. And if we're feeding the solenoids with actuator feed limit pressure, and now we're feeding with less than it's supposed to get, the computer has really no way of knowing that because there's not a pressure sensor in the circuit. The computer is just assuming it's working with that full range of pressure. And if it doesn't get it, then obviously everything downstream from that's going to be affected. So now right now, the aftermarket, Sonnax and TransGo, as of right now, they're not addressing the AFL. Apparently it's not wearing that much on the 8L90. That's the only thing I can assume. Or maybe the addition of this number 10 orifice is keeping it fed with enough steady fluid volume that they're just not seeing pressure drops in this AFL circuit. Because this section right here is not something I've seen before, so I don't think that's very common, where they're actually got an orifice there that kind of keeps the actuator feed limit circuit charged with fluid pressure. And that might have to do with later on, we're going to see this exhaust backfill. Maybe that has something to do with that as well. But either way, maybe that's the reason why that they're not having to address this at all. But TransGo and Sonnax, I mean, Sonnax makes valves, but it's not part of their zip kit, their drop-in kit. So, which kind of tells me that maybe it's not an issue as of right now. Now, one thing to take note of is that if line pressure is below the cutoff point, let's say the cutoff point is 115 psi, if line pressure is only 60 psi, well, this valve would be positioned to let all full line pressure in. So the AFL circuit would be the same pressure as line. But once line pressure finds its way over that predetermined amount, and once again, if I'm using 115 psi as that number, anything over 115 psi, this valve would move over and block itself off. And yeah, it would still be able to find its way in there through that orifice, but apparently this thing consumes enough oil or passes enough oil where the pressure shouldn't still rise above that maximum amount. So where does this AFL pressure go in this transmission? Well, as I mentioned before, it goes to the solenoids, and that's why some manufacturers call it a solenoid feed limit valve, or they might even call it a modulator valve. But regardless, it's a reduced pressure that finds its way to the solenoids. And in this case, you're going to look at these 8L90 solenoids, and you're going to see not every one of them actually receive AFL pressure. Right here up top, our C5 clutch, it actually does see AFL pressure. But some of these others, like the C2, C3, and C4, they're actually fed with line pressure, and the solenoids control line pressure to control their little regulator valves. So, but the way it works, if you take a look at how these solenoids operate, and we'll look at this more on the electrical side of the presentation, but they're fed with actuator feed limit pressure, and that pressure is either going to find its way through the valve or not, depending on the condition of the solenoid. In this situation here, you can see that hydraulic pressure does not find its way through, and that's what this off means on this chart right here, on this picture. So also right here it says NH, that means normally high. That means when I have just laying on a bench, no power hooked up to it, and sitting there in a transmission with completely unplugged, the solenoid's normally high, which means fluid pressure finding its way in is going to find its way right through and come out. The outlet's going to be high pressure, normal situation in a normal state. If it was normally low, like you see some of these listed, like right here that says normally low, that means in its normal state, I could have hydraulic pressure coming in, but nothing's coming out. Low pressure is going to come out. And in order for pressure to come out of this one, I have to energize it. And in order for a normally high solenoid to turn off hydraulically, I have to electrically turn it on. So that's what the NH and the NL mean. So looking at these, they're either going to be controlling line pressure or AFL pressure by duty cycling these solenoids and regulating the amount of pressure that finds its way through the solenoid, and they feed over here to these individual pressure regulator valves for these individual clutches. The hydraulics on this transmission are actually really simple when you stop and look at it, because they've got a solenoid controlling a regulator valve, and the regulator valve controls the clutch directly. So each one of our clutches has its own dedicated regulator valve. So the 8L90 has a kind of unique circuit here. They call this the exhaust backfill circuit. And it's not like some of their other transmissions that they have. Some of their other transmissions use what they call a compensator circuit. So if I have a hydraulic piston, and that hydraulic piston is stroked with line pressure, well, on the spring side, to return that piston, not only do they have a spring, but they use fluid pressure to kind of keep that pushed off. And it's not high pressure or anything like that, but they keep it filled up. And especially our driving clutches that are always rotating, the idea is that if centrifugal force is trying to hold fluid in that drum, and with greater RPM, you're going to actually maybe build a pressure in that drum. Well, if you have fluid on both sides of that, it'll kind of cancel each other out. Well, this transmission doesn't use that. They just use the spring to return the piston. But what they do is they keep the hydraulic circuits filled up with fluid. And it's a very low pressure, like 7 or 8 psi. And it's done through this exhaust backfill circuit. So here you can see on the hydraulic schematic, these are the driving clutches, the input clutches. And you can see they're all yellow right here because none of these clutches are applied in this picture. But what they do is they have hydraulic pressure going into that called exhaust backfill. And as you're going to see here in this little video I got coming up, I tried to figure out how much pressure was in the exhaust backfill circuit, and it's not that much. And the way they feed this clutch exhaust backfill is they've got actuator feed limit pressure finding its way through this orifice 11, and that ends up filling this whole exhaust backfill circuit. And if the pressure starts building up over a certain amount, the blow-off valve that they've got there will unseat and prevent pressure from climbing any higher than, like I said, it's real low. It's like 7 or 8 psi. Now looking at that exhaust backfill circuit that they have a hole in there that's about 290 thousandths of an inch in diameter, maybe a little smaller. And the pressure, or this checkball seats up against that hole in there. And the pressure that finds its way through that hole is AFL pressure. It pushes that ball off of its seat and leaks out after that. And the AFL is fed through an orifice, and then this circuit right here is after that orifice. So it basically is regulating anything beyond that orifice to a pretty low pressure. So I was curious what that pressure was. So at the depth that that ball sits in there, which is at about 1 inch, 220 thousandths from this edge, and then from when we put that spring in there and that clip, it compresses that spring to about 920 thousandths, which is not that much. So I went and compressed that spring to 920 thousandths of an inch. And as you can see, if there's not too much glare, it's about 1/2 pound of force at 920 thousandths of an inch. So when we do the math and we take that 290 thousandths hole and we figure out the surface area of that, which is the pi times the radius squared, and that ends up being a pretty small hole, pretty small surface area. It is 0.066 square inches. And when we divide that into the 1/2 pound of force that's up against that spring, we see that that circuit only requires like 8 psi to push that ball off of its seat and start regulating the pressure down. So really, that backfill circuit only has about 8 pounds of pressure in it. So in case you're wondering, when you're looking at a hydraulic schematic and you see that listed as exhaust backfill, that's only about 8 psi in there. So that clutch backfill circuit's a little unique. I thought it was worth mentioning because I haven't really seen that in any other transmissions before. Now we're going to move over to pressure regulation. You can see this is their oil pump, and it's an off-axis chain-driven pump. Save a little bit of length on that transmission by doing that. And it's also a dual output pump. It's not variable, and that's something that we're used to seeing on most General Motors oil pumps, is having a variable output type pump. But here they don't have that, and they just basically have a dual output pump, and you can see the suction coming in, and then it generates a pressure coming out, and there's another inlet right there, suction coming in, generates pressure coming out. So that secondary line seems like it has a little bit more of a kind of a suction and compression mode, whereas this primary, it looks like it just kind of comes in and almost immediately gets pushed out. I don't know, probably for a volume situation that they've got going on there. But that's a little different, this dual output pump. This is the thick pump gasket. There's a little gutter. And here's the oil pump. And these are parts that are included in the kit. These parts are idiot-proof, at least that I've discovered. They won't let you put it together wrong. Appears they made it idiot-proof. If you put this in wrong, the passageways won't line up properly. and it won't fit into the valve body. So once again, I think it's pretty idiot-proof. But if there's a way to screw it up, I can do it. So how does this pump operate, and how do we regulate pressure in this transmission? Well, the fluid finds its way in from the pan through the filter and feeds into this circuit here. But we actually do have a couple other hydraulic circuits in here, and they're these bypass circuits. And it basically comes from the regulator valve. Once this thing gets into a position where it's generated enough pressure, this regulator valve is going to open up what they call a bypass, where it's going to let any additional line pressure that's generated find its way right back into the inlet of the oil pump. Because if you're delivering more than what you need and you turn around and deliver it to the inlet, you're not going to generate any more pressure. You're just kind of like recycling, if you will, the inlet pressure. And so depending on how they want this transmission to operate, they're showing you two examples. This is example A, this is example B. This would be like low pressure. So the solenoid, the line pressure solenoid, is not delivering much fluid pressure to the bottom of this regulator valve circuit as it's drawn here. And line pressure is going to build up, and that pressure actually finds its way to the end of this shuttle valve. So the pressure that generates in this transmission is going to work against this valve and overcome spring pressure and whatever pressure my solenoid is generating, trying to put there at the bottom. And when it moves it down far enough, you can see we uncover those bypass sections. So you can see secondary pressure finds its way into the bypass, and we could see line pressure finds its way into the bypass right there. It's just barely uncovering that section right here. Now, if I want more pressure in this transmission, you can see like in this example B, they duty cycle this pressure control solenoid to deliver more of this pressure or signal fluid or AFL fluid, whatever you want to call it, to the bottom of the pressure regulator valve. And in this illustration here, they're showing it shuttled all the way up to the top. And what that's done is that's blocked off these bypass passages. So now the fluid can't find its way. The line pressure that's generating, there's no excess yet, so it's not turning around and dumping it back into the inlet. It's kind of cut that off. So instead of turning around and creating a massive leak going back to the inlet of the pump, what they're doing is they're letting the pressure build up in the circuit. And once they build up enough pressure, that line pressure climbs high enough, it will in fact push this valve back down and start opening up these bypass circuits. And if you take a look, something that's unique here is that since it's a dual output pump, you can see the bypass kind of open up at different points. Like this right here, the secondary line is wide open into the bypass. So it's pretty much anything that's, for this low pressure example, anything that finds its way into the secondary line is just going to turn around and find its way right back into the bypass. Where you can see the line pressure is just barely uncovering the bypass passage on the low pressure example. But then when we switch over to the high pressure example, that line pressure cannot find its way into the bypass. It's being blocked by that valve. And then maybe we're just barely uncovering, or we're still blocking, but eventually we'll first start to uncover the secondary. And then if we've got enough volume that we can end up just moving this valve back down. But it's pretty obvious what they're trying to do here. They're using this one portion of this valve or this pump to generate the majority of the pressure. And if needs exceed what the output of the pump is, they'll revert to the secondary side by controlling the secondary portion of this pressure regulator valve and blocking it off so that that fluid can't get dumped off into the bypass as easily. So that's how they're doing it. It's a little different than what they've done in the past. They've relied heavily over the years on variable output or variable displacement pumps, but now they've got this dual output pump, and it seems to be pretty good, pretty cool. I like it. The way this pressure regulator valve works, there's two actually inputs and outputs to the oil pump. So line pressure is present to two different lands, and when there's enough pressure on this side actually being fed through the shuttle valve, through that tiny little hole right there, that pressure is going to work up against the end of this valve. The little plunger in our shuttle valve is going to work up against the end of that valve, and it's going to overcome the tension of this spring and whatever solenoid pressure ends up on this side. So the line pressure that it feeds into the transmission finds its way through the shuttle valve to this plunger, and that overcomes the tension of the spring plus solenoid pressure to move this valve over to the point where it releases that pressure into what they call a bypass, but that's just basically the inlet to the oil pump. and that effectively regulates it. So if this was not receiving the pressure, I mean really all that line pressure is just working across this surface area on the end, if this hole was plugged or if this bore was worn out, there would not be enough pressure, and there would not be enough pressure to overcome the spring and the solenoid pressure, and this thing would always be continuously building pressure higher and higher and higher. So when this shuttle valve wears out, you actually end up with high line pressure because there's nothing to overcome the solenoid and spring pressure to move the valve to its point where it's regulating. This is the solenoid passageway here that's going to be working on the end of this pressure regulator valve to move this valve into its regulating position. This is converter feed right here, and line pressure would exist in these two passages. So you can see line pressure has its way of getting into the torque converter feed. This chamfer on this valve right here feeds line pressure into the bypass section once we are at its regulating position. And if you look, this one is kind of in that valve body land right there. And we also have line on this passage right here. And you can see it's more open, feeding into the bypass. So there's two bypasses, this portion and this portion, and there's two line pressure feeds, this portion here and this portion there. So it looks like this one allows it to bypass first, and then that one, if it strokes further, will bypass second. And right here in this passageway, that feeds the shuttle valve. So the shuttle valve that we have here on the end, when line pressure finds its way into that section, it's going to work on the end of that shuttle valve and move this valve over and eventually get it to the point where these passageways will allow line pressure to dump into the bypass and effectively regulate the pressure. So if you're working on a vehicle that has this start-stop technology or idle stop, where you come to a stop and the engine shuts off, thing that everyone hates, you're going to end up having this surge accumulator in this transmission. So some of these transmissions or some of these vehicles don't have it, and they won't have it. If you don't have it, you won't have it. But some of the vehicles that have idle stop, or all the vehicles that have idle stop, will end up having this. And this is a component that if you look on it, it says, do not disassemble, contents under pressure, will explode, aim towards enemy, something like that. But I took it apart. It's not that big of a deal. You just be careful with it. You keep it clamped. I clamped mine in the arbor press, and I went through this in the video for the valve body section, the overhaul video, valve body. And you take these Torx bolts out and you can pull it apart and clean it. I think it's a good idea to take it apart and clean it. Now the kits that I have didn't come with seals for this, so that's something to take into consideration. But the way it operates is that when the vehicle is running, when the engine's running and we're generating pressure in the transmission, there's going to be a feed. It's going to feed line pressure into that accumulator. It's going to unseat that check ball. If you follow that around, it fills this void right here and strokes this piston up against spring force. That way when the vehicle shuts off, the engine shuts off, and now I don't have my oil pump running anymore, they can energize that solenoid and they can deliver that fluid pressure to the 1, 2, 3, 4, 5R, and then they can also fill some of these line pressure circuits up with fluid pressure. And like I said, it doesn't have to be a lot of pressure. We just need to keep these circuits primed and filled with something. So that way when you take your foot off the brake and the engine fires up, pressure can build up instantaneously. We don't have to deliver any volume to anything. We just need to build pressure. So that's kind of the goal of that. And so yeah, that's the reason why it's kind of got these dashed lines out there, is because it may or may not have it. On a hydraulic schematic, some of these little these little crosses that they've got, or stars, they usually indicate that it may or may not have it. And that's basically how this thing operates, surge accumulator. So now looking at this portion of the valve body, this is the solenoid portion of the valve body, and you can see I've got all my solenoids listed here, the torque converter clutch and the 2, 3, 4, 6, 8, and what they have, looking at all these different solenoids, they've got the solenoid, and then they've got a regulator valve, and then a spring. And all these springs pretty much are the same. They all look the same, except for this one right here, the torque converter clutch solenoid and regulator valve. It's got some thicker coils, it's a little shorter, and has higher tension. And so just keep that in mind, because when you look at them all next to each other, they pretty much look the same. And we'll cover those here in a second. This is the 1, 2, 3, 4, 5 boost valve. converter feed limit valve, and that's something that is addressed in some of the aftermarket kits address that. This is really the only real accumulator we've got in the transmission. We got this 13567 accumulator in spring, and you can actually get a valve in a kit, or not a valve, but a replacement accumulator in a kit for that. The line pressure solenoid is down here, and we've got these on-off solenoids, the default solenoid and the 12345R boost solenoid. Those are all located in the solenoid valve body. Another different view of this same valve body, this here is the solenoid side. I kind of had those laid out there again for you. But I did put a note up here in 2018, 2019-ish. They actually did change things. I know I've got a 2018 unit here, and it does have that. On the 23468 regulator valve, you'll notice it's completely different. The design of it, so it's basically this one right here. That valve is like much thicker all the way through, and they've got an identifying slots. They got 2 slots. Most of them have nothing, or they have 1 slot, like a big, almost looks like a screwdriver slot they have on the end. But they put 2 of them on that. But you can see it stands out as a completely different valve, and so they end up changing some things. They change some spring tensions, valve body, spacer plates, and all that stuff. So make sure if you're dealing with that 2018, 2019 year range that you're getting the right parts. Best to order parts. If you're doing it through the dealer, use your VIN number. So like many manufacturers, this valve uses a tiny little hole right there in between these valve lands, and that pressure, the line pressure that finds its way into that section, finds its way out through the end of that valve and works on the end of that valve to move this, to shuttle it. And it's going to work with that tiny little spring that they've got that goes on the end. So that spring pretty much helps line pressure move this valve. So all these pressure regulator valves work pretty much the same. In the little clip I'm going to show you here in a second, I use the torque converter clutch solenoid and the torque converter clutch valve to explain how pressure operates. But it's the same with the torque converter clutch as it is with all the different clutches that we have in the transmission. Basically what they have is they have a solenoid. It's going to receive either AFL or line pressure. That solenoid is going to manipulate pressure to work against the end of that regulator valve. And right now, like you can see, line pressure can turn around and find its way right into that clutch circuit. And the line pressure that finds its way in there is going to shoot its way through the end of that valve and work across the surface area in the back of this valve to move it over to basically regulate or cut its own supply off. So it'll build pressure up to the point, at least during the shift, they're going to use this to kind of control how pressure rises in the clutch. They're going to control how the line pressure can find its way into this clutch circuit. Now, if this solenoid was de-energized, we don't have any hydraulic pressure at all in here, and this spring returns this valve into its resting position, this exhaust backfill would find its way into that clutch. That's the reason why all the released clutches, except for one, have exhaust backfill going to the clutch circuits. But when they operate the solenoid, they're basically going to regulate how much line pressure can find its way into that clutch circuit. And of course, once you're in the gear, they just let full line pressure go to the clutches. But they're going to manipulate the solenoid to manipulate the pressure to the clutches during the shift to get the clutch feel the way it's supposed to be. And if you remember what we talked about with like the mechanical operation and the overhaul, that these are clutch-to-clutch units. So as I apply a clutch during a shift, I have to release a clutch. I can't release a clutch too soon or apply a clutch too late because then I'll have nothing applied and it'll flare. But the same thing holds true. I can't hold a clutch on that I'm releasing for too long, or I can't apply a clutch too quickly, or else I'll put the transmission in a bind. So it's real precise how they have to operate these solenoids and these clutches, and everything's tied together. The solenoid operation, the pressure that it finds its way over to these regulator valves, the clutches themselves and the clutch pack clearances, the computer has to be doing its thing like it's supposed to, line pressure needs to be where it's at, and AFL pressure needs to be where it's at. All these things need to work in harmony, and if they're not, you're going to end up having flares and binds and weird shifts. Now, all I can say is if you have a lot of shifts that are giving you problems, you're probably dealing with something overall, like a line pressure issue or an AFL pressure issue. But if you're dealing with one specific shift that's dealing with one solenoid circuit or one clutch circuit, you'd be focusing on these areas specifically. Going more off that hydraulic and that clutch control, this is kind of what it would look like. And I have labeled out these passages here. That's the feedback passage. When line pressure finds its way in through that hole, and finds its way to the end, it's going to work into this feedback circuit, which is basically just pushing against the end of the valve to move it over and put it in a position where line pressure can't find its way into the clutch anymore. And then if they want more pressure going to the clutch, the solenoid pushes on the end of this valve with hydraulic pressure, and that moves the line pressure or the valve over so line pressure can find its way back into the clutch circuit. And then it goes through the tiny hole, goes to the back, and then builds up pressure until it can shut itself off again. Now, if this solenoid is completely off, kind of like it's drawn right now, the backfill circuit can find its way into that clutch circuit. So that way we can keep that circuit filled up with 7 or 8 psi when it's not being used. In this situation here, we've got full line pressure going to a clutch. So I've got my line pressure, it's finding its way in, right into that clutch circuit. The exhaust backfill is completely blocked off. It's not being utilized at all anymore now. And yeah, there is pressure going here to work on the end of the valve, but the solenoid pressure that I've got on this end is high enough to the point where I can't overcome it with whatever line pressure I got working across that small surface area that I have at the end of the valve. And as I mentioned, not all of these valves are the same size. Pretty much everything that's on the solenoid side, it is 530 thousandths, thereabouts. Yet the reaction side, the side that the clutch pressure and spring pressure are going to work with to kind of cut the pressure off in a sense, those are different sizes. A lot of them are 442 thousandths, but we've got some of them that are 423 thousandths. So there are 2 different size valves. And like I said before, the only spring that's different between all of these is the torque converter clutch solenoid utilizes a little stiffer spring than the rest. It's kind of hard to tell. It's like looking at this, can you tell which spring is different from the other? And you might be able to notice, but that one right there is a little thicker and a little shorter than the rest. So kind of as a summary, solenoids S1, 5, and 6 are fed AFL. Solenoids S2, 3, 4, and 7 are fed with line pressure. The torque converter clutch has a slightly smaller and thicker spring, like right there. And the S1 and S5 have a slightly smaller reaction land. So the actual reaction land that the spring works with, that's a little bit smaller on the S1 and S5. So S6 is torque converter clutch pressure and S7 is line pressure, but S1, 2, 3, 4, and 5 is clutch 1, 2, 3, 4, and 5. It's the way that this regulator valve works, and in this case, it's the case of the torque converter clutch solenoid. And the valve is going to be sitting here as such, and in this passage right here is going to be line pressure. This passage is the torque converter clutch, and then this passage is exhaust. So what ends up happening is when they want, right now line pressure can't get anywhere because it can't get past that spool. So what happens now is when the solenoid that lives behind it here, it receives pressure from the basically line pressure, and it's going to deliver that to the end of this valve. And it's going to stroke this valve over, and when we start letting line pressure into the torque converter clutch circuit, that pressure finds its way through that little hole, comes its way to the back of the valve, and works with the spring to return it and close it off to the point where no more pressure can get in. If they want more line pressure, they'll duty cycle the solenoid higher and build more pressure up on this end of the valve, on the solenoid reaction land. That will move the valve over, let more line pressure into the torque converter clutch circuit. That additional pressure will find its way over and help with that, or work with that spring to move that valve closed again. So it's always going to be a competition between the solenoid pressure on one end of the valve and the torque converter clutch pressure that found its way to the other end of the valve, plus whatever that spring is helping it with. So basically these springs are little helper springs. So that basic premise works with all these different regulator valves for all these different clutches. So really they're doing the same thing as far as delivering pressure from the solenoid to the end of the valve. The pressure that it lets into the circuit works with the spring to close that circuit off. The more solenoid pressure that they create, the more pressure that'll find its way into that clutch circuit until it can close itself off. So as I mentioned before, I use this torque converter clutch regulator circuit as an example, but all these valves pretty much operate the same. So the fundamentals that I covered right there is going to apply for any one of those clutch regulators as well. Like some of the other GM transmissions, this transmission also uses these little solenoid accumulators. You can see that one's worn out pretty bad. See how shiny it is right there? It's not supposed to look like that. So the aftermarket has come up with fixes for that. We've got drop-in replacements. Sonnax makes these little sleeves with springs and pistons that kind of fit in there. And TransGo and Sonnax, they both also offer a reamable option where you can ream out the bore and drop in a new plunger and valve. You can see they've got a variety of them. So they're tiny little accumulators, what they are. They're mini accumulators that operate with the solenoids. So they dampen out the solenoid operation. So it is important to look at those. So if I'm having an issue with any one particular clutch, like the 1278R or the 45678R, possibly that I'm going to be dealing with, like use this one, pick on this for example, if I'm having an issue with my 3/4 shift, maybe it's quite possible that I'm dealing with an S5 accumulator, which is right there. So if I take that out, and if that happened to look like that, then possibly, quite possibly, I found the root cause for my issue. Because if that solenoid is trying to create pressure to control its regulator valve, but my little accumulator is worn out and that's all leaking out past it, that means it's not working the regulator valve like it's supposed to, and I'm not going to get the shift quality that I'm expecting. So it's important to inspect these things. When we go through and do vacuum checks, you can actually vacuum test these different circuits here that have that to see if there's excessive leakage behind any of those. The check balls on this transmission are plastic, so you definitely want to replace those. And if you look at the kits all come with new check balls. And GM's been using these plastic check balls for years now, 6L80, 6L90, and they do have a tendency of shrinking, and it's more than likely they're spinning in there and they're slowly shaving themselves down. So you don't want to take the chance of putting it back together with some used check balls that might be a little smaller than they should be. Just go ahead and put the new ones in. And you're going to see the valve bodies have these little bathtubs or single spots for check balls. But you're also going to find that depending on the year of the unit, you might not have check balls in certain spots. And you also might find out that if you have start-stop, you might have check balls in certain spots, whereas if you don't have start-stop, you won't have it at all. So definitely pay attention to the location of the check balls. I will tell you this, Sonnax has a nice chart on their website. When you go to, like if you pull any of the instructions down for their zip kit, you're going to see a nice layout that explains where check balls are supposed to be located. So for this valve body, I'm actually only going to vacuum test the clutch regulator valve for C3 because you actually, and Sonnax provides, or not provides, but sells a special tool that allows you to vacuum check these. It basically replaces this valve with a dummy valve, and they have it for the different size valves that are in here. And the reason why they do that is because there's that tiny hole that's in there, and if you vacuum check this, vacuum is going to leak out through that hole. But what I'll do is I'll just cut a little strip of electrical tape and wrap it around and cover that hole. But I'm not going to do that on every single one, but I figured I'll go ahead and do it on the C3 because that is the clutch that was failed on this transmission. So the other ones I went ahead and put back together and put in. So you can see that these are the ends, that's the spring end of all these pressure regulator valves. And that's the one that you're either going to want to use their recommended vacuum test tool, or you're going to have to close off that hole. So I'm going to put on the C3 that I'm using, this one right here, I'm going to go through and put a piece of electrical tape on the valve, something you probably don't want to forget to take off when you're done with it. And then some of these others might have special instructions too. And there's actually also on this converter feed limit valve, there's also a little passageway there that you're supposed to plug off. And then with those accumulators, we can go ahead and place some suction on top of those to see if those are sealing up or leaking. So we're calibrated with our vacuum gauge. We're showing 25 inches and roughly 5 inches. We're going to go through and check all of our accumulators. Start with this one here. Good seal, looks good. Next, that one's low. That one's definitely a bad one. We'll mark it. This one is questionable. Nope, that one's actually really good. This one's a massive leak. Only pulling 1 inch. This is definitely a bad one right here. This one's not sealing up very well either. Getting about 5 inches, 11 inches, 15 inches. Both of those are pretty bad. That one's probably pretty good. So good. We got 4 bad ones, 3 good ones. So for a shift valve, we're going to want to plug off that hole. I'm going to use a piece of electrical tape. And hopefully this will do a good enough job to seal that off. Actually seals up pretty good. Got 20 inches on the solenoid side. Got 24 inches on the reaction land on this side. We can go ahead and check our 1365 accumulator while we're here, right through that passage. 24 inches on that, that's a good seal. That's a pass. Then our lube regulator valve is going to be that little guy right there. Got about 18 inches. So as you can imagine, a vacuum test can save you a lot of money. Now, it might not help the solenoid situation out so much if you suspect a solenoid is bad. If you do suspect a solenoid is bad, you're supposed to put a whole new valve body in because you cannot get individual solenoids. You might be able to pull a solenoid out of a core and do some swapping, but it's recommended against that because these solenoids are all characterized by flow rates, and they're taught to the computer what those flow rates are when you go through and install the valve body. You put what they call a PUN number in there, a part unique number, and we're going to learn about this in the electronics lecture, which is coming up next, the next video after this. But those PUN numbers teach the TCM what flow rates in solenoid characterizations your valve body has. So if you're swapping parts around, you're going to lose that characterization. And that's actually a good thing to talk about if you're pulling these solenoids out. Making sure they go back in their same spots is very important too. But at least now we know that if we vacuum test this, if we find poor results, that the aftermarket, like Sonnax and TransGo, they've gone through and they've created fixes for the hydraulic side of things, for the valving side. So at least we know we don't have to trash an expensive valve body because of a accumulator bore is worn out, or because a pressure regulator is not sealing like it should, or a torque converter limit valve. If you're not into vacuum testing yet, I do have, and I'll try to put a little link up here somewhere, basically a link to a video that I've created where you can make an inexpensive DIY vacuum test station. Costs you about $100 or something like that. So in reality, if it saves you from buying one valve body, it'll pretty much pay itself off. So to summarize this lecture, what we learned about was this actuator feed limit, how important that valve is to the operation because it's kind of upstream of everything else. Feeds all these different, or not all of them, but feeds some of these different solenoids. So if you have an issue in the actuator feed limit, you're going to have an issue with clutch control, and you're going to have shifts, binds, flares, all kinds of problems. We also learned that the TCM is going to control a solenoid. That solenoid controls a valve, and that valve controls a clutch. So issues anywhere along that stream is going to cause a problem. And we also learned about our solenoid accumulators and how, as we saw on the example that we had up there, they like to wear out. And they're there to dampen out these pulses from the solenoids, and if we had issues with that, we could ultimately have issues with the clutch control. Now in the rebuilding particulars video, and likely in the modifications video, we will talk about things that you can do with the aftermarket kits to restore those solenoid accumulators. We looked at exhaust backfill and how unique that was, how they keep these clutch circuits filled when they're not applied. We keep them filled with low pressure. And we also looked at our pressure regulator valve and the shuttle valve and how it operates a little different than our typical GM pressure regulator valves and boost valves that we're used to. And also, along those same lines, as we looked at their dual output pump, it resembles that Jatco CVT pump, uses those little vanes, and also talk about this in that rebuilding particulars video because they have an issue with that pump not wanting to prime, especially if you replace a valve body and those little vanes are kind of stuck in there. So in the modifications video and in the rebuilding particulars video, point that out, show you ways around that. Also showed that in the overhaul video, but hey, you can never repeat stuff enough because sometimes it's the second or third time before you finally get it. So And that's about it for this one, so we'll see you on the next one, which is the electronics lecture, where we talk about electrically how this transmission operates.